This is part 2 of a series on the error backpropagation. In this video, we will look at backpropagation along multiple paths. This video was produced in Korean and translated into English. My voice was generated by AI text-to-speech. In the last video, we looked at backpropagation on a single path and interpreted its meaning. In this video, we'll look at the backpropagation along multiple paths and explore the algorithms for finding gradients. Let's take a look at backpropagation along multiple paths using the simple neural network below as an example. This neural network consists of an input layer, a hidden layer, and an output layer. The output layer has multiple neurons and uses the softmax activation function. This neural network is for a multi-class classification. Let the classes of the desired output Y be 0, 1, and 2. Each class is 1 hot encoded. Class 0 is encoded as 1, 0, 0. Class 1 is encoded as 0, 1, 0. And class 2 is encoded as 0, 0, 1. The subclasses Y1, Y2, Y3 are the desired outputs of the output neurons. The outputs of each neuron are Y-hat1, Y-hat2, and Y-hat3 respectively. And the loss of each output neuron is measured by cross-entropy like this. The losses for each output neuron are L1, L2, and L3 respectively. The total loss will be L1 plus L2 plus L3. This is the cross-entropy for one piece of data. And the forward propagation is similar to what we saw in the previous video. The output X2 of the hidden layer is passed to multiple output neurons. X2 is responsible for all losses, including L1 and L2. Because if X2 is wrong, all losses are affected. W2 is responsible for loss L1, and W3 is responsible for loss L2. If W2 is wrong, L1 increases, and if W3 is wrong, L2 increases. Since W2 contributed nothing to L2, W2 is not responsible for L2. Likewise, W3 is not responsible for L1. Therefore, W2 and W3 can be updated via backpropagation along a single path, as seen in the previous video. W2 is updated like this using the gradient of L1. Since W2 is independent of L2, this is 0. So instead of L1 in this equation, we can just write L. W3 can also be updated using the gradient of L2 in this way. Since this is 0, we can also just write it as L. However, the way we update W1 is different from the way we update W2 and W3. W1 is responsible for both L1 and L2. If W1 is wrong, both L1 and L2 are affected. Therefore, W1 must be updated considering both the gradient of L1 and the gradient of L2. The gradient of L1 is backpropagated through W2, and the gradient of L2 is backpropagated through W3. This can be represented visually as follows. The gradient of L1 is backpropagated along this path, and the gradient of L2 is backpropagated along this path. And these gradients are combined here. Therefore, when updating W1, we need to consider the combined gradient. Let's take the following neural network as an example. The output layer has one neuron and uses the sigmoid activation function. This neural network is for a binary classification. There are two hidden layers. The first hidden layer has one neuron, and the second hidden layer has two neurons. The loss L is defined as the binary cross entropy. The gradient of the loss L with respect to W1 is backpropagated along these paths. This path goes through W4 and W2, and this path goes through W5 and W3. So W1 is updated in this way using the chain rule. The yellow path is expressed as a chain rule like this. This path goes through W4 and W2. The green path is expressed as a chain rule like this. This path goes through W5 and W3. Now let's update W1 using some numbers. Input data point X is 1.0 and the desired output Y is class 1. The initial values of W are all 0.5. Let's assume there are no biases. And the activation function of the hidden layer is rel_u. And the activation function of the output layer is sigmoid. When forward propagation is performed, this network outputs y hat 0.5622. Then the loss L becomes 0.5759. The gradient of the loss L with respect to y hat is minus 1.7787. And the gradient of y hat with respect to Z4 is 0.2461. Now let's plug these numbers into this equation. Learning rate alpha is set to 0.1. Then W1 is updated from 0.5 to 0.5219. Let's update the parameters of this neural network just once using TensorFlow. We'll cover this code in more detail later in the TensorFlow series. For now, let's take a quick look at the code and check the results. Input data point X is 1.0 and the desired output is also 1.0. The initial values of the parameters W are all set to 0.5. We compute the binary cross entropy and use it as the loss L. And we write a function that performs forward propagation. This function returns y hat, the output of the neural network. Then we compute the gradient of the loss L with respect to each parameter. TensorFlow's gradient tape computes accurate gradients through automatic differentiation. We'll look at this in more detail in the next video. We use these gradients and apply gradient descent to update each parameter. Since this process is not repeated, each parameter is updated only once. Let's check the update results. These are the parameters W4 and W5. And these are the parameters W2 and W3. And this is W1. You can see that the updated W1 matches well with the result on the left. Next, let's look at the activation function and the vanishing gradient problem. In the simple neural network on the left, W2 and W1 are updated as follows. When updating W2, the derivative of the activation function F2 is used. And when updating W1, the derivative of the activation function F1 is additionally multiplied. When there are multiple hidden layers, the derivatives of the activation functions are multiplied sequentially. If there are 10 hidden layers, the derivatives of the activation functions are multiplied 10 times. If the derivative of the activation function is less than 1, multiplying the derivative value 10 times will produce a very small value. In lower hidden layers, this value is very small, so W's in those layers are hardly updated. That is, W's in upper layers are updated a lot, while W's in lower layers are hardly updated. This increases the loss and prevents the neural network from learning. This is called the vanishing gradient problem. If there are 5 hidden layers, the activation functions are all sigmoid, and the derivatives are all 0.2. Then 0.2 is multiplied 5 times. Then we get this small value. On the other hand, if the derivative of the activation function is greater than 1, the gradient increases exponentially as it goes down the layers, because this value is multiplied many times. This is called the exploding gradient problem. To alleviate these problems, ReU activation function is widely used in hidden layers. The gradient of ReU is either 0 or 1. If it is 1, then the gradient propagates well to the lower layer. If it is 0, the gradient will not propagate. However, in this case, the output values of some neurons in the hidden layer become 0, which causes the dropout and regularization effects that we will look at later, which can prevent overfitting. In the worst case, if the output of all neurons in the hidden layer becomes 0, the gradient cannot propagate to lower layers. This is called the dying ReU problem. This problem may appear if the learning rate, alpha, is large or the bias is large and negative. This is because they make the weights negative and the output of ReU 0. To alleviate this problem, you need to lower the learning rate and prevent the bias from becoming too large. You can also try using the leaky ReU or soft plus activation function. Finding the gradient of the loss L requires a differentiation algorithm. Since the expression of the loss L varies depending on the neural network structure, an algorithm that automatically differentiates it is required. In deep learning, the amount of training data is huge, and the number of parameters is also very large. Also, the parameters are updated over a very large number of iterations. Therefore, an algorithm is needed to find the gradient of loss L as quickly and accurately as possible. Let's look at the differentiation algorithms shown below. The first algorithm is symbolic differentiation, which finds the differential function by directly manipulating the mathematical expression. For example, Mathematica differentiates the sigmoid function as follows. This method can find the exact derivative, but depending on the shape of the loss L, the result becomes very complex and time-consuming. So it's not suitable for deep learning. The second algorithm is numerical differentiation, which we looked at in the Artificial Neural Networks series. There are forward difference and center difference methods. This is an algorithm to find approximate derivatives. Finally, there's the automatic differentiation algorithm. There are forward derivative trace method and reverse derivative trace method. This is used in deep learning because it not only finds accurate derivatives, but is also fast. We will look at this in more detail in the next video. Let's take a brief look at numerical differentiation. We've covered this before, but let's take a quick look at it again. The forward difference method is like this. It measures how much the function f changes when x changes by h. Here h is a small value. Center difference method is like this. As you can see from the results below, the center difference method is more accurate. If h is too large or too small, the error will be large. And if h is appropriate, the error is small. We can see that among the two methods, the center difference method has a smaller error. At this point, the derivatives of this function, using the center difference, are as follows. H is set to 10 to the power of -4. If h is set to 10 to the power of -15, the results are as follows. The results will vary depending on the value of h. Finally, let's use numerical differentiation to update the parameters of the previous example. Since we directly measure the gradient of the loss L with respect to the parameter W using numerical differentiation, there is no need to apply backpropagation. If we measure the change of loss L with respect to W1 using the center difference method, it looks like this. Using this gradient, we can update W1 as follows. I wrote a code to update the parameters of this neural network using numerical differentiation. I will skip the explanation of the code. The results are as follows. The previous results using TensorFlow's automatic differentiation were as follows. You can see that the two results match well. However, this results may vary depending on the value of h. Also, this method is time-consuming because the predict function must be run every time each parameter element changes. So far, we have looked at the error backpropagation on multiple paths and looked at gradient finding algorithms. In the next video, we will take a closer look at the automatic differentiation algorithm.